So for this completed Taylor series for cosine of x at x equals 3 pi, here's our series. So now what we want to know is how many terms do I need to get a certain level of accuracy? So we have a magic formula that is amazing. So this is Lagrange, whoever he is. He did a lot of work in physics. There are the Lagrange points in orbital dynamics. So he did a lot of physics, but history is not my gig, at least not math history. Probably pretty interesting character, though. Got his name on a lot of stuff. Lagrange equation. So here it is. So what's amazing about the Lagrange equation is he doesn't just say that the remainder has to be less than something, the error has to be less than something. He tells you exactly what the error is, which you might think, if I know exactly what the error is, why don't I just correct the error? Well, it does have a trick to it, which is that the error is the n plus first derivative of f at some point c over n plus 1 factorial times x minus a to the n plus 1. Now in this equation, for a specific value, we know the x and the a. So for our example, x is 10, a is 3 pi. We know all the derivatives. We know what n plus 1 factorial is. The problem is the c. We don't know what the c is. The only thing we know about c that I forgot to write in here is that c is somewhere in the interval xa or ax. So the reason I have to write two intervals is because we don't know whether x or a is larger. So with a equals 3 pi and x equals 10, the x is larger. But if I used a equals 3 pi and x equals 9, then the a is larger. So I don't know which way to write the interval. And most books just say c is between x and a. But I wrote it that way. So an interesting comparison is, here's our standard Taylor series, right? It's the nth derivative of f at a, not c, but a, over n factorial times x minus a to the n. All right, that's your Taylor series. All this is if I add up finitely many terms, like say 10 of them, this would be the 11th term of the series, except the a shifts to c, and I don't know exactly where it went. I only know that the c is between x and a. All right, so that is the Lagrange equation. Now, from that we get an error bound, which is, so the idea with the Lagrange error is, I don't know what the c is, but I probably know something about the n plus first derivative of f and how it behaves over x and a, and I might be able to know what is the largest this could possibly be. So let m be the maximum value of the n plus first derivative of c over one of those two intervals, over ax or xa. So again, some books say between x and a, avoiding that problem. Then the absolute value of the remainder, because now we don't know whether the remainder is positive or negative, is less than or equal to the absolute value of that maximum of that n plus first derivative over n plus 1 factorial x minus a to the n plus 1, which is just the rest of the same stuff. All right, so this is the form we're normally going to use, and the key is to say, how do I know what this m is? Well, my given function is cosine. In fact, all of the derivatives of cosine are either cosine or sine. So since I know that that the absolute value of cosine of any number is less than or equal to 1, and the absolute value of sine of any number is also less than or equal to 1, the most this m could be is 1. So for our series, at x equals 10, what I'm going to have is the absolute value of r sub n is less than or equal to the absolute value of that m is just 1. And you'll see the idea is just to get what that maximum value could be depending on the function. So I'm actually I have x, I could put the 10 in right away, but I didn't, so let's just keep going where I'm at. Minus 3 pi to the n plus 1 over n plus 1 factorial. And we wanted that error to be less than or equal to 10 to the negative 7th power to get 7 digits of accuracy. All right, so at x equals 10 then, I can say that absolute value of r sub n is less than or equal to. So also with, if x is 10, then 10 minus 3 pi is positive, and n plus 1 factorial is positive, and I've forgotten my, have I forgotten? No, I haven't forgotten anything. Okay, so n plus 1 factorial is positive, so everything is positive here. So that means I can drop the absolute value. I'm always looking to do that if I can. So then my numerator is just going to be 10 minus 3 pi to the n plus 1 over n plus 1 factorial. So now I just have to solve that that's less than or equal to 10 to the negative 7th power. So solving this inequality is now what it's all about, solving this inequality. So I've used my Lagrange error bound, and I've set it less than or equal to the accuracy that I want. Now, how do I solve it? Well, you can play around with trying to solve this inequality. There isn't really any very direct way to do it, but what we can do is solve it with a table. So we will solve it with a table. And so you can see here, I've already set up my y equals to be 10 minus 3 pi to the x plus 1 over x plus 1 factorial. That's just this right here, this expression. And yeah, we have to use a table. We can't use a graph because of the n factorial. We can't do factorials of anything that's not a natural number. So we'll look at how the table is set. The table is set to start at 1, and the delta table has to be 1. It's really the only important things there. And we can go say, let's hit the table. All right, so now what we're looking for is a number that's less than 10 to the negative 7th. So I can scroll down here. I got 3 times 10 to the negative 7th, and then I got 1.9 times 10 to the negative 8th. So this is the one I want. I want 1.9 times 10 to the negative 8th because that's less than 10 to the negative 7. So that's going to give me n equals 8. So n equals 8. We need 8 terms. All right, now, but here's the trick. In our original series, some of the terms were 0. So when I look at this table as I laid it out right here, right? This is n equals 0 right here is the first term. And then n equals 1 is the 0 term. N equals 2, n equals 3, n equals 4. So where's n equals 8? N equals 8 is not going to be 1 over 8 factorial. Actually, it is going to be 1 over 8 factorial. So n equals 5, 6, 7, 8. We're going to have the one with 1 over 8 factorial. But the trick is in the way that I set up this sum, this is 2n up here. This n up here is not the same as this n right here. So this 2n is what I want to be 8. So the sum that I want to go up to is actually 4, and that's really 8 terms of the series because every other term was 0. So that's a little confusing. When I go to actually compute the sum, so if we go to the calculation window, and here's my sum. See, I set my sum to be n equals 0 to 4 instead of 0 to 8, because once I get 4 here, then my my 2n right here is going to be 8. And that's when we say, when we talk about the n in this equation, it's the original n. Essentially, we modified the n here in order to drop out all the 0 terms. So watch for things like that. So our 8 terms is really the sum from n equals 0 to 4 of negative 1 to the n plus 1 times 10 minus 3 pi to the 2n over 2n factorial. Right, because that will get us to the 8th power here, which is really what we're talking about there. All right. So when we do that on the calculator, here's what we get. Negative 0.8390715,302. Here's cosine of 10 for comparison. And so if you look at where they differ here at this place. So how many decimal places is that? 1, 2, 3, 4, 5, 6, 7, 8. We have exactly 7 decimal places of accuracy. Now, by the way, that wouldn't have to happen because this is only a maximum of the error, so we could have gotten better. We could have gotten a better estimate. But so it's really sort of satisfactory that using this number of terms prescribed by the error bound gets us exactly the accuracy that we were looking for, using 8 terms. So then you can, once you've got the table set up, you can also answer more questions like how many terms, oh, yeah, we're here, yeah. How many terms would be needed to get an accuracy of 10 to the negative 20th power, because of course we want to get that kind of accuracy at least. All right, so all I have to do is look at my table, so we'll just go back to the table, all right, and say when do I get 10 to the negative 20th for my error term? And I just keep scrolling down here. There's 10 to the negative 19th, there's 10 to the negative 21st, so I need n equals 17. So I need 17 terms, n equals 17 terms. All right. Now, by the way, the odd terms are all 0. So what we're going to actually use in the calculator is the sum n equals 0 to round this down and take half of it, 8. And that's going to give us the 16th power. And that 16th degree polynomial is going to be equal to the 17th degree polynomial because the 17th degree polynomial was 0, of whatever my blah, blah, blah series was. All right. I'm not going to do that one on the calculator because in the calculator, you won't be able to see if you have 20 points of accuracy because they don't display 20 digits. But you often, for applications might want that level of accuracy, especially if you're using this value then to compute other values.